Hello, I want to welcome you all to this special session of the FIL of the International Book Fair in Guadalajara, in which I have the pleasure of welcoming not only you, but also Professor Venki Ramakrishnan, a very, very distinguished scientist who won in 2009 the Nobel Award together with two other colleagues, Dr. Ada Jonath and Dr. Tom Stites, for their work on the crystal structure of the ribosome. This might seem like a very esoteric subject to the non-scientific audience, but as time goes by, we are increasingly becoming aware, all of us, of the key role that the knowledge and understanding of subcellular structures have to understand everyday life, but also peculiar events like the current pandemic we are facing. Today we will have the pleasure of having a conversation, and they will concentrate on the Spanish translation of Benki's book.
Good evening. It's a pleasure to be here. And I'm sorry, we might have had some connection problem, but I'm back online, and it's very good to see you again, Antonio.
But I have to say to the audience that I actually had the chance, the opportunity to know you long before that by reading your papers. Octavio Paz, the poet, once said that poets have no biography; they have their poems we read. But the same is probably even much more true for scientists. We can have a conversation with Galileo or with Charles Darwin or with Madame Curie, regardless of the times.
That's true. Yeah, that is true. We scientists tend to be known by our work, not so much by our personal lives or our hobbies or interests. It's really our work that makes us known or sort of recognized.
Which makes your book a very interesting reading for everyone, because you mix in a very capable way. You mix your own personal life, your quest for a position in science, your attempts to understand very successfully, one has to say, the crystal structure of the ribosome, together with the excitement of scientific discovery.
Yes, although I should say the book is not really an autobiography. For example, I don't talk about my childhood or growing up or my parents or my school friends. It really starts with my desire to become a scientist, and sort of it's a scientific story, not an autobiography. So it's very much in the sort of light of other scientific books which describe a quest for a particular problem. Some people have compared it to the double helix, but without the gratuitous nastiness. So I've tried to be frank like Jim Watson, but not, tried to be nasty like him in some ways.
It appears to me, I think it appears to everyone, that it's not really in your character to be a nasty scientist, but what comes out very rapidly from the very first page is the intellectual obsession, the drive to understand what is now recognized as a major component of all modern life.
Yes, that's true. Although, as you know, since you've read the book, it was not a straightforward journey. I started off, I came to America when I was 19, hoping to become a physicist. And of course, even in physics, there are hierarchies. And of course, at the pinnacle are theoretical physicists who explore the basics of the universe and so on. Somehow, during my first few years of graduate school, I realized that it really wasn't for me. And I also realized physics was in a very difficult situation. It was very hard to make progress. And on the other hand, biology was at a very, very exciting stage, somewhat similar to where physics was in the early 20th century. So after finishing a PhD, as you know, I went back to graduate school, which my father, when he found out about it, was quite disapproving. You know, he thought his son was going backwards. And, so it was not a straightforward situation. And of course, by the time I switched fields, I was married and I had two children, including a newborn. And sort of moving with this family from one place to another as you sort of developed your career was also not straightforward. And I have to say, I'm very lucky in the partner that I've had, my wife Vera, who humored these efforts.
Ever have any doubts about how wise your decisions were in moving fields or moving from one place to the
I
other?
think so, I think so. Actually, it's a funny thing. I mean, most scientists have underlying some sense of insecurity about, we hope things will work out, but we're never sure things will work out because research is an uncertain endeavor. If we knew the answers, it wouldn't be research. And so when I switched to biology, I had to learn a whole new vocabulary because the vocabulary of physics is actually based on a few principles and you build out. Whereas in biology, you have to actually know a lot. You have to know a lot of terms, a lot of phenomena. And so I wasn't sure whether I was cut out for it. And one particular time was when I finished my postdoctoral fellowship at Yale, which is where I first started working on the ribosome. I applied to 50 interviews, 50 job applications, and I got absolutely no interviews, not a single interview. And so I was wondering, what have I done? I've switched, I failed in one field and then tried another field, and now it looks like I'm going to fail in the second field. So I've had some low points. But to young people, I say, I always had backup plans, so my backup plan was, if I couldn't get a job, I could become a computer programmer because in those days, in the 70s and early 80s, it's not like today where every high school child knows how to program. It was still a kind of valuable, uh, sort of experience to have, valuable expertise. And so that was one possibility. And another possibility was that I thought, well, if all else fails, I can go and teach high school. I can become a science teacher in high school. And when I think about it, actually, neither of those professions would have been bad. Actually, if I'd gone to Silicon Valley in the 70s or 80s, who knows, I might have been a billionaire now. But leaving that aside, I think teaching in high school is also an incredibly important job. I mean, all of us who became scientists were influenced by a teacher at some point. And so I think if I had gone to become a high school teacher, I would have been okay. I would have tried to be a good teacher. I would have tried to figure out new ways of teaching science. So this idea that we only have one goal, and if that doesn't work out, we're a big failure. I think we should get away from that sort of idea.
I'm delighted to hear you praising the work of teachers because I think that never before in the history of humanity have more instruments in our hands to teach the computer, the book, the web, and so on. But never before, I'm afraid, has the role of teachers been more despised or unappreciated by modern societies, which I think is a
Oh, it's
disgrace.
yeah. It is really terrible, and people think they can offload teaching to computers and so on. I think computers can be a good aid, but without that human interaction where a teacher is, taking a personal interest in the individuals in their class, I think there'll be something really badly missing. And so And I agree with you. They're very underappreciated, and I also think they're in most countries they're also underpaid, and that means that people who normally might be attracted to teaching often don't go into it.
But I think that both of us agree, and probably many people in the audience agree, that one cannot understand the role of a scientist today if he or she is not involved in teaching, in research, and in doing outreach activities. And for me, the best example is the extraordinary lack of understanding that we are facing now because of the pandemic, of the coronavirus pandemic. Clearly, when you see some sectors of society opposing vaccination, we don't even have a vaccine for the against COVID-19, but we already have groups that are opposing it. When you see these right-wing movements in many parts in the world of people opposing scientific research, or when you see this new age kind of hand waving in which they say, "Don't touch nature, it's forbidden. You should not disturb the cosmic order." Clearly, science has to play a key role in today's world, and this key role must be defined by these three activities: research, teaching, and outreach.
Yeah, no, it is true. It's odd that you mentioned that because, as president of the Royal Society, I've been involved in convening a group to look at various problems related to COVID and providing additional advice to the government. But interestingly, just last week, I was in a conversation with Stephen Fry, the actor. He's a comedian, actor, and writer who has a real deep interest in science, interestingly. And we were discussing exactly this problem, the problem of misinformation and even disinformation in science, and what to do about it. How can we cope with misinformation and pseudoscience in an age of the internet and social media? This is not going to be an easy problem to solve, I'm afraid.
I quite agree with you, and it's a universal problem in our global society. But let me go back to this part of your life in which you switch fields. Um, Clearly, from reading your book, one gets the impression that you were feeling an outsider for some time. Do you still feel an outsider in biology, or do you feel that the community has come to an understanding that we need to have a multi-field, multidisciplinary approach to big issues like the nature of the ribosome?
Yeah, no, I think this feeling of an outsider is part of my psyche, and because it has to do with my personal history. I was a South Indian, a Tamil, who moved to North India at the age of 3, where I didn't even speak the local language. And then at the age of 19, I moved to the US, and I went to not one of the top universities. I went to a state university in Ohio, and then I tried to transfer to biology. So at each step, I was a kind of outsider. In other words, not somebody following sort of the main track for that particular profession. And then, I was a physicist turned biologist, and I was using this rather strange physical technique. Then I eventually moved to England, where again I became an outsider. So I think that feeling of being an outsider never quite goes away. And it's a little bit strange now because I'm very well established. I'm the president of the Royal Society in Britain. Nobody could be more establishment than me. I'm a fellow of Trinity College, and I work at one of the most famous labs for molecular biology in Cambridge. But in spite of all that, I still have that feeling of being an outsider somehow. And of course, people will laugh, but it's an internal feeling. Now, you mentioned the multidisciplinary aspect. A lot of science is becoming multidisciplinary. My own work involved a combination of X ray crystallography, which is really a physical technique and synchrotron radiation, along with an understanding of the biochemistry and biology of the ribosome. So it was very much multidisciplinary, in which all of my training actually helped me, the different parts of my training. And a lot of science is becoming like that. If you look at genomics, genomics now involves very sophisticated mathematics and statistics and computer science. So, and there's a lot of machine learning and artificial intelligence being used to discern patterns in genes and so on. So I think this multidisciplinary concept is going to become more and more important. I don't know if there's a need to particularly prepare for it, except what I advise people, young people, is to get a very broad education. In other words, don't just do biology and forget about physics and mathematics or vice versa. Uh, Try and take the four core subjects: physics, chemistry, biology, and mathematics. These are the basis for all of the sciences. And I think that would be my approach and my advice to a young person.
I'm delighted to hear you say that because I remember that when I first applied to the position I have now in the university many, many years ago, I had to undergo an interview with a number of professors that were part of the jury. And they asked me to please indicate to us in the lab the microbiological instrument that you see here. And I pointed out the computer, and they were quite taken back. But then I was one of the first to be doing sequence comparisons and so on, which has been the thing I've been
Exactly.
working. So yes, I quite agree with you. The other thing that comes to me to my mind right away is the famous story which many people are not aware of. You know how familiar all of we are with the representation of proteins as ribbons, and as it happens, that came from an extraordinary woman. Unfortunately, I don't recall her name right now, who was an
Uh,
artist.
J-
And
Jane Richardson.
that's correct, Richard. She was the most. We wanted to invite her to Mexico, but now it's sort of difficult. And it was quite extraordinary that she having a background in painting, in art, was able to come up with an extraordinary representation of a protein structure and eventually also RNA structure that is instrumental for understanding, for teaching, for learning, for designing new molecules, new biological molecules, which in fact brings me to your probably favorite subject, which is the three-dimensional structure of the ribosome. We see it mostly as ribones, but the distinguishing, understanding those ribones is key to a proper comprehension of what must be one of the oldest key components of contemporary cells.
Yeah. So, without different kinds of representations, the ribosome would be just a collection of balls of atoms. Each atom would be represented by a small ball or a marble, and you would have 500,000 atoms. So you'd be just looking at a big collection of atoms, and you would have no idea how to interpret this object. And so you're right, this simplified representation that Jane Richardson, she's from Duke University, first did for proteins, and then other people adapted it for RNA and DNA. That turned out to be very important. In fact, going back all the way to DNA, just that single diagram in the Watson and Crick paper, which shows the simplicity of the double helix, that had a huge cultural and scientific influence. And oddly enough, it was done not by a scientist, it was done by Odile Crick, who was an artist. She was Francis Crick's wife. So again, this idea of art representing some scientific reality like a molecule has actually allowed us to conceptualize what the molecule might be doing and how it might work. So I think that's actually a very important point.
We speak about the arts, Nowadays, we are forced to lecture and to teach using the screen, the computer screen. But I still have to see among my fellow scientists something as original as you can see from, for instance, for the ballet performances or the concerts in which the people are playing or dancing in their home, and they combine the things in an extraordinary way, which reveals a creativity that scientists not always have.
No, I know that. And I think, you know, talking about presentation, we scientists now rely far too much on PowerPoint and these very, very sort of corporate style diagrams. And I remember when I was younger, even very famous professors would come and lecture, and they would just come to the blackboard and draw a few things, and so you could actually see the process of their thought. That's the part that you don't get when you present things on a computer. It's already finished. You don't see the process that went into creating a PowerPoint slide the same way as you do when somebody is sketching something out on a blackboard. So I think there is that issue. And in structural biology, visualization is a big problem. I mean, when we solved the ribosome, one of our biggest problems was how to present ideas of this complicated molecule in the illustrations in our papers. And that took a huge amount of time, almost as much time as to write the text.
I'm delighted to hear you say that, but for a number of reasons. But you mentioned structural biology. Of course, whether a macroscopic or a subcellular level, a structure in biology is determined not only by physical and chemical constraints, but also by history. Or in other words, it's determined by evolutionary biology, the evolutionary history behind each structure. What are your perceptions nowadays about the complexity of the history of the evolution of the ribosome? It could have not have started to being something as complicated as we see today.
No, absolutely. And, yeah, the point is, there is, I describe in the book, a long-standing dilemma, which we're finally coming to grips with. And that is that the ribosome is a machine, a big biological molecular machine that makes proteins, but itself consists of proteins. So the puzzle always was, if the ribosome makes proteins and itself is made of proteins, where did the first ribosome come from? It seemed like a chicken or egg problem. And Francis Crick was the first person to say that, well, maybe early ribosomes had no proteins at all. They were made only of RNA. At the time, RNA was not known to be capable of function like an enzyme in terms of carrying out chemical reactions. It was thought to be an inert kind of scaffold or an inert carrier of the genetic message. So nobody knew what to do about Crick's idea, and yet nobody had any solution to this puzzle. Then, when it was discovered that RNA could catalyze chemical reactions, people like Harry Noller had already suggested that maybe the RNA in ribosomes was important. But as soon as RNA catalysis was discovered by Czech and Altman, people like Harry Noller, developed biochemical evidence to suggest that maybe the key functions of the ribosome were in its RNA component. And when the structure was solved, of course, all the key functional sites were made almost entirely of RNA, suggesting that maybe the ribosomes started off with a small core which was made of RNA, and then this core grew, and then some of the proteins it made stuck to itself, and gradually the ribosome evolved. And it didn't stop there. For example, bacterial ribosomes are much smaller than uh, our human ribosomes. And even in humans, we have a mitochondria, which are descendants of bacteria, But even their ribosomes are much larger and more complex than bacterial ribosomes. So the ribosome, even after it got to its modern form, kept on evolving so that ribosomes from different domains of life are fairly divergent in the number of proteins they have, in the size, and so on.
Which is absolutely fascinating, because I'm afraid that our conversation is coming to an end because of the time limit. But what you are describing is precisely what is one of the key issues in biology. You have to keep changing so the thing will be kept the same in many ways.
Yeah.
There is a very famous novel by Italian prince, the Gepard, the Gattopardo, in which he says everything must change so the situation will be kept the same. And biology always
Yes.
moves like that. Venki,
Yeah.
I think the conversation is coming to an end. But before we do, what will be your advice to a, let us say, 13-year-old girl that wants to be a scientist, or a 19-year-old teenager who is not sure that he wants to be a basketball player or a mathematician?
Well, I would say, first of all, science is one of the great triumphs of humanity. It is as big a triumph in our culture as art or literature or music. We know amazing facts about the universe that if we went back 200 years and told people, all the things we know now, they would either think we were crazy or they would think we were magicians. That is how amazing it is. And so the life of a scientist, although it's uncertain and sometimes can be full of anxiety, it is actually a very rewarding uh, work, because every day you go to work not knowing what you're going to find out. And there are not many professions like that. To the 13-year-old girl, I would say, in the past, science was a male dominated profession. But there are so many brilliant women who have gone on to do great science that you should not let any of that past history bother you. And rather, you should try to get a broad based foundation so that you can go on and do the kind of science you actually like. Okay. And to the teenager who wants to decide between a basketball player and being a scientist, let me say the odds of you making it as a basketball player and being a big star are much, much lower than your odds of being a productive scientist and having a rewarding life where you won't burn out at the age of 30, but you can keep on going well into your 60s and 70s and still have excitement in your work. So that's what I would say.
Thank you for saying that. And what, as you were speaking about the advice to the 19-year-old teenager, what came into my mind was what once a very, very dear friend of mine, Emil Zucker-Kandel, the one who came up with the idea of comparing sequences and found that molecular evolutionary stories, once told me. He came from a very, very distinguished family in Vienna. He took musical lessons with Maurice Ravel. His grandmother was the best friend of Klimt, and Albert Einstein gave him a letter so he could establish himself in the USA and so on. And he told me that when they had to move to France, and then from France to Algiers, because it was a Jewish family, and during the war they had to emigrate right away. And when he was in Algiers, André Gide, the famous writer, told him, "Do you want to be a musician?" Because he was a very good piano player. "Or do you want to be a scientist?" And then Emile decided, okay, I would probably be a mediocre musician, but I can try to be a good scientist. And he played the whole field single-handed. So what you are saying is precisely quite correct. Uh,
Yeah.
Before saying goodbye to you, let me thank you once more for the chance of seeing you again, of talking to you, of conveying these extraordinary ideas to the audience, especially to the younger audience. as they are stated in your book, now available in the translation, of course. A very good translation, I have to say. I went through it very carefully. And in closing, let me say that just to remind people of the significance of the work that we do in science, and especially people like you, that people may think have no application. We now realize that one of the first interaction that the COVID-19 virus, that the coronavirus has, when it invades a cell, is to go right away into the cell ribosome and stopping it from making the cell proteins. So here we have a wonderful example, a dramatic example, if you wish, of the significance of unexpected significance of scientific work, scientific discoveries. Dear Venki, thank you so much. It's been a
Thank
pleasure.
you.
Take care, and let us hope to
Yes.
meet in person in the very near future.
Thank you. I'm so delighted that my book has been translated to Spanish. As you know, I studied Spanish for many years, pero ahora he olvidado casi todo mi vocabulario, see? So, but, but the point is, I was hoping to come to Mexico, and really it would have been a chance also to refresh my Spanish, but I will have to wait. But I hope that when the pandemic is over, I will have a chance to visit and maybe do some book events in Mexico. Thank you very
I
much.
promise I can try to organize something like that, Venki. Take care, best regards, and until next time. Bye bye.
Thank you. Bye bye.